Hello and welcome to this video on solving compound inequalities involving the word or. Alright, and this is a follow-up to other videos I put up on compound inequalities involving the word and. Alright, so this is just a second kind of compound inequality where you have two inequalities with a connecting word or. And I have several examples, and I'm just going to get into them and we'll talk about how to solve these. So the first example I have for you, and in each one I'm going to be asked to solve the inequality, solve the compound inequality, then express the solution using what's called set builder notation and interval notation, and also graph the solution set, and being that there's only going to be one variable appearing in my compound inequalities in each example, the solution set will be graphed on a single number line for that single variable. Alright, so let me get into the steps. Alright, so here's my first compound inequality, right? You have x plus 3 is less than 1 or x minus 2 is greater than 3. Alright, so what are we looking for here? What are we trying to do? Alright, when I'm asked to solve an equation or an inequality, I'm trying to find numbers that'll make it true. So what would make this entire statement a true statement? So here are the steps I'm going to go through off to the side here. First, I'm going to solve each of the inequalities in this statement separately. Alright, so we're going to find what the solution sets of this inequality and this inequality. Right. So I'll do them in different colors because then we're going to do something with these solution sets after we solve each one separately. So the first one, x plus 3 is less than 1. The only thing I would need to do here to get x alone to solve for x is subtract 3 from both sides. And this is just subtraction, and when you add or subtract, the direction of the inequality does not change, so the left side's x, and that is still is less than, and then 1 minus 3 is negative 2. Alright, so the solution set, now I'm going to call the solution set of the first inequality just the set A. Alright, you can call it wherever you want. Alright, but I'm going to say set A is the solution set of this first inequality. Okay, and it's all values of x that are less than negative 2. Right, so all values of x such that, little bar there, such that x is less than negative 2. Right, and what I've just written here is called set builder notation. Right, so later on I'm going to also write in set builder notation the solutions of the entire inequality, the compound inequality. But for right now, we have just this one set I'm calling A of the solutions of the first inequality. Alright, then in another color, so it's like this magenta or fuchsia color here, I'm going to solve this inequality. Alright, so x minus 2 is greater than 3, simple, just add 2 to both sides. And again, when you add or subtract the same number to both sides of an inequality, the inequality direction does not change, so it would still be x on the left is greater than still, and then 3 plus 2 is 5 on the right. Alright, so I'm going to call the set of solutions for this second inequality, I'm going to call that set B. Alright, again, you can call whatever you want. And the solutions of this second inequality are all the values of x such that x is greater than 5. Alright, so again, what I have here is called set builder notation for the solutions of this second inequality. Okay, so I've done for part 1, solved each inequality completely, alright, separately, and then after that, when we had the word and connecting the two inequalities, we solved each one separately and then found the intersection, right, the overlap of the two solution sets. And I've put up a previous video on finding the intersection or the union of two sets, so you can look for that or find other videos on intersections and unions. But here I have the word or, and the word or implies that we're going to be finding the union of the solution sets. Alright. Okay, so the union, really what we're looking for is, when I say find the union of these sets, we're going to be finding what numbers satisfy either the first inequality, make true, right? Satisfy either the first inequality or the second inequality. Oh, that's right, second with a 2 there. Second. The second inequality or both, right? So you got the word or here twice. So this is sometimes referred to, this or, when you see it, sometimes referred to as the inclusive or. All right. And by inclusive or, again, simply means I'm in either this set or both. All right. So it's very, very loose, the restrictions on this. Alright, so here's a little picture. Alright, we're going to find the union of these two sets. So here's a number line for you. Alright, so there's a real number line representing all the real numbers. I got 0 somewhere separating positives from negatives. And in the same colors, I'm going to draw a picture of these sets, these solution sets A and B. Alright. So set A is the set of all numbers less than negative 2. Right, so negative 2 would be to the left of 0. There's negative 2 on the number line, let's say. And all the numbers less than negative 2, but not negative 2 itself. So to indicate that negative 2 is not in that set, I'm going to put a little open point, a little hole up above it. That tells me that negative 2 is not in the set. And then all the numbers less than negative 2 are negative 3, negative 4, negative 5, all these numbers over this way. So there's set A in the orange. All right, and then below the number line here, set B in the fuchsia or magenta, whatever color this is all the numbers, the solutions of this second inequality are all the numbers greater than 5. Now 5 would be over here, right to the right of 0, positive. And it's all the numbers greater than 5. So not 5 itself, right? So I'm going to put an open point here in line with 5. To indicate that 5 is not a solution to the second inequality. And all the numbers greater than 5, all the numbers that satisfy this would be 6, 7, 8, 6.2, whatever you want, 5.1. All these numbers to the right of 5, right? There's set B. And then the solutions of our compound inequality, right? The original whole statement, the whole thing with the word or there. The solutions of the compound inequality, the whole thing, is going to be made up of the set A union B. Right? As I've said, I've put up a video on this before, but this little union symbol, right, means we're taking the union of the sets A and B. When I called set A, right, the solutions of this inequality, called set B, right, the solutions of that second inequality. So what is this set? I'll write it here in that set builder notation. So it's the set of all values of x such that, right, so all values of x such that, little bar, or a colon here, a little double dot, 2 dots. And then after the bar, the description of the solutions. So remember, to be in the union of A and B, I'm either going to be in A or in B or both. Let's look at my picture. All of these numbers that are less than negative 2, those all belong to A. So they belong to the union. So all the numbers of all the x's that are less than negative 2 are in the union. Or and just writing the word or, and this is that inclusive or, and look at all these numbers here. All these numbers greater than 5. All these numbers belong to the set B. So they belong to the union, right? If you're a number in A or in B or in both, you belong to the union. So all the numbers less than -2 belong to the union, or all the numbers greater than 5 also belong to the union. And that's it. So it's all the numbers x that are less than -2 or greater than -5, and there aren't any numbers that are in both, right? So you don't have to include those, right? There's nothing there. But this is it. Here's a perfect description in set builder notation. And I'll write that up again here. This is called set builder notation with the little curly braces at the ends, and then what are we talking about, and then a little bar, and then the condition on what we're talking about, what variables involved. This is set builder notation. Great, so I'm going to put that in a box. Right, here are the solutions of this compound inequality. All right. Great. So that's one part of it. Right? We're asked to express the solution using set builder notation. Then we're also asked to I like to make graphs actually before I usually put things in set builder. So here's a graph of the solutions. All right, so we have here's the number line. Sorry, it's not perfectly horizontal. I apologize. I should use a ruler. Throw 0 there to separate positives from negatives. And then, what are all these numbers that are described here? Right? They're all the numbers less than -2. So that's all these numbers here, right? Not including -2. Or all the numbers greater than 5 are also a solution in this set, right? And here's the numbers greater than 5, again, not including 5. So there's a graph, a picture of all the solutions of this compound inequality. And finally, we were asked to write the set in what's called interval notation. And if you're unfamiliar with interval notation, just look it up. I'm sure you can find a video describing. I've put up a video before describing how to write sets in interval notation. So if you're unfamiliar with that, just look it up, or read in your book somewhere on interval notation. Look it up in the index. I'm not going to go that in depth into it here. All right, I'm just going to write it. So look at my graph. I like to look at the graph of a solution set when I write the solution set in interval notation. Notice there are 2 pieces of this graph, right? There's a big break in it, and there are actually 2 pieces, right? This piece over here, all the numbers to the left of -2, and this piece over here, all the numbers to the right of 5. So for each piece, we're going to have to write an interval, right? So every piece of the graph gets its own interval. So this first piece over here, now how you write an interval is what's the left end of that piece? What's the low end? Well, this little arrow here indicates that there is no low end. There is no lowest value in this piece of the graph for this part of the solution set. So to indicate in an interval that there's no lowest value, there's no left end, we write the concept negative infinity, right, to indicate that there's no left end. You're going this way forever, to the left forever. It's not a number, right? That is a concept, that is an idea, that I'm going left forever, right? The negative infinity is not a number. And then comma, and then what's the right end of that piece, that first piece of the picture? That's at -2. All right, and then you cap these off, and you cap them off with either a parentheses or a rectangular bracket, depending on whether or not the number at the end actually belongs to the set. Well, I said a second ago, negative infinity is not a number, so it actually doesn't belong to the set. It's not a solution, so we put a parenthesis on it to indicate that negative infinity is not a solution because it's not a number. And then -2, the right end, is -2 a solution? Well, we said no, right? -2 is not a solution, so again a parenthesis on that. All right, so there's the interval representing this first piece of the graph. And then we have the word or, right? Or, and then a big space, or. Now you can write the word or or you can actually draw that union symbol again. Sorry, that's nothing. Just ignore this. Ignore that dot. You can just write the union symbol again for the word or. So I'm either in this set of solutions, there's numbers here, or the numbers over here are the solutions of this inequality. And so over here, what's the left end? 5, comma, and there is no right end on this second part. So I put infinity. Again, that's a concept, it's an idea, that's not a number. So 5 to infinity. And parenthesis on the 5 because it's not a solution. Parenthesis on the infinity, always on infinities because it's not a solution, because it's not a number. And this is what we would call the interval notation for this solution set. All right, it describes the same. This describes the same set of numbers that this picture does, and they both describe the same set of numbers that are described in this set builder notation. So all the numbers less than 2 are solutions, or all the numbers greater than 5 are solutions. And you can double check. Now go back to the original inequality. Here it was, way back up here. This x plus 3 is less than 1, or x minus 2 is greater than 3. And check. Pick any number you want that's in this set. Pick a number less than -2. Pick a number greater than 5. And see if one of these or both of them, as long as one of them is satisfied, we're okay. We're in this union, right? It's considered a solution of this compound inequality. So let's say -3. -3 is in this set, right? -3 is less than -2. Plug it in. -3 plus 3 is 0. 0 is less than 1. This inequality is satisfied, so I don't even need to check the other one. As long as one of them is satisfied, we have a good solution. So -3 is a solution. How about 6? Well, let's see. 6 plus 3 is 9. Is 9 less than 1? No. But we're okay. We can still see if the other one's good. All right? Just because that one's not good doesn't mean the whole thing's not. Plug in 6 over here. 6 minus 2 is 4. Is 4 greater than 3? Yeah. So 6 is a solution of the compound inequality. Remember, for these ors, as long as one of them is satisfied, the whole thing is true. It's considered a true statement. So great, we do have a pick, and again, check other ones. Just plugging in 2 numbers doesn't prove anything. Check a bunch of other ones if you want. But any number less than 2, -2, or any number greater than 5 will satisfy this or statement, this compound inequality. It'll satisfy at least one of these 2 inequalities. Wonderful. All right, and that's all we're doing. All right, we're solving each inequality separately. Then finding the union, right? The union of those 2 solution sets. And it's really simple. Union's really loose, right? The union of 2 sets are all the numbers that are in the one set or in the other set, or in both, right? Very inclusive. All right, so I've got several other examples up here for you where I'm doing the exact same stuff over and over and over again, right? Just to hammer it home. Okay, so this one I have 3x plus 1 is less than or equal to 7, or 2x minus 3 is greater than 9. All right, so I'm going to solve. First, I will solve each one individually, and again, I'm going to do them in different colors so I can write their solution sets in different colors. So here I would subtract 1 from both sides, right? That would leave me with 3x is less than or equal to 6. Then I would divide both sides by positive 3, right? And this division by a positive number, so the inequality direction will not change. So that's x is less than or equal to 2. Alright, so again, I'm going to call this set A, alright, the set of all the solutions of this first inequality. X is, it's all the values of x that are less than or equal to 2. Alright, wonderful. Same thing for the or, and then I have the solutions to this one too. Alright, for this one I'd be adding 3 to both sides, right? And you have 2x on the left is greater than 12 on the right. Dividing both sides by positive 2, so the inequality will not change. X is still greater than, and then 6. 12 divided by 2 is 6. So again, I call this set B, and it's the set of all values of x such that x is greater than 6. And I'll even, draw a little picture. Right, here's a number line for us, 0 somewhere, and again, A in the same color. All the numbers less than or equal to 2. So here's 2, or be to the right of 0. 2 is actually a solution this time. 2 is in there. 2 is a solution to this first inequality because it's all the numbers less than or equal to 2, and 2 is equal to 2. So I put a solid point, or you could put a rectangular bracket, but to indicate that 2 is a solution of this first inequality. And then all the numbers less than 2 are to the left of 2, right? So there's set A, drawn in a picture. All right, and then same color for set B, the magenta thing. All the numbers in this solution set for the second inequality are greater than 6. Now 6 is to the right of 2. Pay attention to where numbers belong. And all the numbers greater than 6, but not equal to 6. So again, I put an open point or a hole below 6 here to indicate that 6 is not a solution of the second inequality. Or you could put a parenthesis. And then all the numbers greater than 6 are to the right of 6, 7, 8, 9, and so on. Right, there's set B. All right, and what we're looking for here, again, the word or is involved, right? And when the word or is involved, that implies we're finding the union of these two solution sets. So what's A union B, or the union of sets A and B? So the union would be all values of x such that, I'm going to write this in all our solutions in this set builder notation. It'd be all the values of x such that, and again, union is not very restrictive at all. If you're a number in set A, then you're in the union. If you're a number in set B, then you're in the union. And if you're in both, you happen to be in both, you're in the union. It's very, very unrestrictive. So all of these numbers that are less than or equal to 2, they're in the union. Because they're in set A, they're in the union of A and B. So x is less than or equal to 2. And then again, the word or, please write the word or. And then all the numbers, because I'm seeing union here, so the word or should be involved. Right? And then all these numbers that are in set B, all the numbers greater than 6, also belong to this union. And that's it, right? And again, there's no numbers that belong to both. This is it. All right. So a perfect description of all the solutions. All right, so I'll put this in a box. These are the solutions of the compound inequality. And you can go ahead and check it out. Take any number less than or equal to 2. 2, 1, 0, negative 5.5, whatever. Take all these numbers here, plug them in, and it'll satisfy this whole statement because at least one of them will be true, right? As long as one of them or the other one or both are true, you have a solution. And the same thing, take some numbers greater than 6 and plug them in for x here and here. And as long as one of these is true, at least one of these is true, the whole thing is true, and you have a solution. All right, so there's the set builder notation for our solutions. And then again, we're asked to make a graph of the solutions and also write the solutions in interval notation. And you're going to see that this is pretty similar to my first example now. Right? Graph, here's the number line, real number line, got 0 somewhere, and all the numbers less than or equal to 2 are in the union. So 2, all the numbers less than 2 or equal to 2, so 2 is in there. And all those numbers are in the union, great. And also all the numbers greater than 6, but not equal to 6. Right? So again, I put an open point above 6 here. All the numbers greater than 6 are also in the union. And here's a picture of my union of these two sets, a picture of all the solutions of this compound inequality that we started with. And then interval notation. And just as with my first example, right, there are two separate pieces here. So I'm writing two separate intervals and connecting them with the word or the the union symbol, which represents the word or. So this first piece, right, there's no left end, so again that's symbolized by negative infinity, comma, the right end of this first piece is the number 2. Negative infinity is not a number, so it doesn't belong to the set. You put parenthesis on that. We said that 2 is a solution, all right, and because it is a solution, put the rectangular bracket. All right, make little 90-degree angles here. All right, a rectangular bracket around that. Or, right, and again, or is symbolized by this, the union with, the union symbol. And then, this other piece, if you write an interval, the left end is at 6, comma. There's no right end, indicated by a positive infinity. 6 is not a solution, so parentheses on that. Infinity is not a number, so parentheses on that. All right, and then here is the interval notation for the same graph, the same set of solutions that we have seen already. Remember, all three of these things, the set builder notation with the description, the graph, the interval notation, all three of these represent the same set of numbers, represent the solutions of this inequality here. Right? Pick any of these numbers that you want, and this inequality, this whole statement, will be a true statement. At least one of these will be made true. Great. Either this one, or both. All right. So I've done it again. All right, let's do it a third time. I've got several. Doing the same procedure every single time. All right. We might eventually come into a case that isn't like the first two examples. Well, let's see. All right, I'm going to keep going. All right, so here I've got 2x minus 3 is greater than or equal to 1. Or, so the word or is going to be in here throughout, and it implies I'm doing the union of two sets, right? 6x minus 5 is greater than or equal to 1. So same thing, same procedure. I'm going to do this in one color, solve each of these individually. So this one I would add 3 to both sides, and we have 2x on the left is greater than or equal to 4, and then divide both sides by positive 2, and we have x is greater than or equal to 2. All right, so again, set A, right, the set of all the solutions of the first inequality is the set of all x values such that x is greater than or equal to 2. All right. Or, and then we have this other inequality, 6x minus 5 is greater than or equal to 1, a different color I pulled out. I would add 5 to both sides here, giving me 6x is greater than or equal to 6. Then divide both sides by positive 6, and leaving me with x is greater than or equal to 1. Alright, so set B, and again I'm going to use the same letters I've been using. Set B is the set of all the solutions of this second inequality, and it's all values of x such that x is greater than or equal to 1. Right, and just like the last couple examples, draw a picture of these two sets of solutions on a number line. All right, so here's the real number line. Got 0 somewhere separating positives and negatives, and in orange I will put set A, all the numbers greater than or equal to 2, right? So 2 is over here, to the right is 0, let's say, somewhere over here, right? All the numbers greater than 2 or equal to 2. So 2 is a solution, and all the numbers, greater than 2 are 3, 4, 5, that's all this way. So there's set A, right? In orange there, that arrow. Set B, change colors. The number 1 is involved. Now, don't forget, place things in the proper place on the number line. 2 is here, so 1 would be to the left of that. 1 is smaller than 2. 1's closer to 0. And then this is the set of all numbers greater than or equal to 1. So 1 is actually a solution of this second inequality, right? It's equal to 1. And all the numbers greater than 1 are 2, 3, 4. Those are to the right. Alright, so this is, there's set B, right? All those numbers there. So this is a little different than the previous two examples, because in the previous two examples, my two sets were pointing in opposite directions when I drew them on the number line. Here, these two sets of solutions for the first inequality and second inequality are pointing in the same direction. Alright, so now I'm going to find their union. Alright, where the word or is involved again, so I'm finding the union of the two sets. Alright, so now look at these. this time there are actually numbers that belong to both, right? In fact, all the numbers 2 or greater belong to B as well, right? You see that? 2 is in B right there. And all the numbers greater than 2 are also in B. So A, you can just lump into B, right? All those numbers belong to the union. And all the numbers that are in B that aren't in A, right? All these numbers here from 1 to 2, they belong to the union as well. So hopefully you can see that all the numbers in the union are all the values of x that are just greater than or equal to 1. Right? Because look, all the numbers greater than or equal to 1, these are in B, and all of these are in both. So all these numbers here belong to the union of A and B, right? Because they're either in A or in B or in both. So I don't need anything with the word or here, right? If they're pointing in the same direction, then there should be some overlap and you can kind of lump one set into the other. I hope that makes sense. So the numbers in the union, the solutions of this compound inequality are simply all the numbers greater than or equal to 1. And I'll again put that in a little box here. Here are the solutions described in that set builder notation. Alright, and then just like with the others, put a graph. And we'll do a graph, a picture of these solutions. So here's a number line, 0 somewhere, and the solutions are simply all the numbers greater than or equal to 1. So 1's in there, and all the numbers greater than 1 are over here. Right, there's a picture of all the solutions. Right. And now for the interval, again, different than the first two examples. Because in the first two examples, there were two separate pieces. Here there's only one part of the graph, right? There's nothing outside here. There's no break in the graph. There's no hole in the graph. There's only this one piece. So I'm only going to be writing one interval. And that interval, right, when I look at this piece of the graph here, the left end of it, the low end is at 1, comma. There is no upper end, there is no right end, so I indicate that with an infinity symbol. Positive infinity, going to the right forever. So this is everything from 1 to the right forever. 1 is a solution. So a rectangular bracket around that, right, indicating that 1 is a solution. And again, infinity is not a number, so it can't be a solution. Always a parentheses on that. All right, so there you go. There's the interval notation for my solutions. And all three of these, I've said it the last two examples, all three of these represent the same set of numbers, this set of solutions to my inequality. And you can check it out, right? There's the original inequality, this compound inequality, connected by the word or. Pick one, pick any number bigger than 1, and at least one of these inequalities will be satisfied. This one, or both. Right? Again, check as many numbers as you want that are greater than or equal to 1. On the other hand, if you pick a number less than 1, neither of them will be, right? Because again, only numbers that are solutions will satisfy at least 1. Anything that's not a solution, like 0, right? If I put in 0 here, you get -3 is greater than or equal to 1. That's not true. Put in 0 here, you get -5 is greater than or equal to 1. That's not true either. Anything that's not a solution won't satisfy any of the inequalities in the or statement. Right? Great, but I did the same stuff, right? You solve each one separately, and then find the union. What numbers belong to one set or the other set or both. All right, so let's look at, I've got several more. All right, same procedure. This one has some fractions in it, so ooh, right, it's scary. So this is 3/4 times the quantity x plus 4 is less than 6, or 3/2 times the quantity x plus 1 is greater than 15. Now you can do these, take several approaches at this. You can distribute the 3/4 and then multiply everything by 4 if you don't like fractions, and then you would subtract, then you would subtract 12 and then divide by 3 and all that. And I see a quick way to do this right now with just a couple steps. So this, I'm gonna solve each one separately. And you got the word or involved here. So there's going to be a union of two sets involved. So this last one I'm going to divide by 3/4, which is the same thing as multiplying by 4/3. So I'm going to write that. I'm going to times 4/3. Times 4/3. Right, dot, little dot, times. Because when you multiply 3/4 by 4/3, that'll be 1. Right? The 4's would cancel, the 3's would cancel, you'd have 1. So all I'm left with on the left side is just this factor of x plus 4. So just x plus 4 now on the left is less than, and I multiplied by a positive number, so the inequality stays the same direction. Then 6 times 4/3 would be 24/3, and 24 divided by 3 is 8. Or you could say 3 in the denominator goes into 6 twice, and then you'd have 2 times 4, or 8. And then I would simply subtract 4, and then you have x is less than 4. Alright, so again, I'm going to call this set A, the set of the solutions to this first inequality. It's the set of all values of x such that, those values of x are less than 4. Okay. And then something similar for the inequality over here. Again, you can distribute the 3/2 and then multiply everything by 2 if you don't like denominators, and then and then you would subtract 6 divided by 3. All right. But I think an easy way is just get rid of this factor of 3/2 by multiplying by 2/3, right? That's the same thing as dividing by 3/2, right? Remember, division is the same as multiplying by the reciprocal. So dividing by 3/2 is the same as multiplying by 2/3. And I would do the same thing over on this side. Again, the little dot means times, right? That'll make this into 1, right? 3/2 times 2/3. That'll make that into 1. So I'm left with just the factor of x plus 1 on the left is greater than, because I multiplied by a positive, still greater than. And then 15 times 2/3 would be 30/3 if you multiply the numerators, and 30 divided by 3 is 10. Or you could say 3 goes into 15 5 times, and then 5 times 2 is 10. Either way, that's 10 over there. And then I would subtract 1, and we're getting x is greater than 9. All right, so again, set B here is all the values of x that are greater than 9. All right, all the solutions of that second inequality. All right, and I see the word or is involved again, so I'm doing the union of these two sets. Again, before I get into that though, I think it'll be easy to determine what the union is if I look at a picture of these two sets. All right, so the solutions of the first inequality are all numbers less than 4. So 4 is to the right of 0. All the numbers less than 4, but not equal to 4. So that's these numbers to the left of 4 here, but again, an open point at 4, not 4 itself, right? And then the solutions of the second inequality are all the numbers greater than 9. 9 is to the right of 4, and that's greater than 9, but not equal to 9. So there's set B down here. And now we're back into a scenario that's exactly like the first two examples I showed you, where you see the directions of the sets are in opposite directions. There's no overlap, right? There aren't any numbers that are in both of these sets. So very simple, the union. The union is going to be made up of this set and this set, right? All these numbers or all these numbers, right? And all of them belong to the union. All right, so the union of these two sets, and I'll write it in set builder notation, will be all values of x such that all of these numbers belong. So all the numbers that are less than 4, or, right, because they are separate, or, and then all these numbers belong too, right? Any number that belongs to A or B or both belongs to the union. So or any number greater than 9. And there you go, and that's how you leave it. This is it with the word or there. Perfect. This is a nice description of all the solutions of my compound inequality, and you can check it out. Plug in any number less than 4. Plug in any number less than 4. This first inequality will be true. So the whole thing will, right? Again, as long as this one or both are true, the whole thing is considered true with the word or in there. Plug in a value greater than 9. This inequality will be true, so the whole thing will be considered true because at least one of them is. All right. And then let's make a make a graph and write an interval, and you can hopefully see that it's just like those first two examples. I just had some fractions in the beginning. All right, so here's a graph. Got a number line. We got all the numbers less than 4, or 0 somewhere. All the numbers less than 4, but not equal to 4. All right, so there's those numbers. Wow. Wow. Okay. Oops. Let's put 0 over here. So ignore this. Sorry about that. That's two little errors today. Ignore this. 0 should be to the left of 4, right? So 0 is here, 4 is here. So all the numbers left of 4, and I guess I could just call this 9, but there's 9, all the numbers greater than 9. Right. So here's a picture of all that of these numbers that are described in the solution set. All right, all the numbers less than 4, all the numbers greater than 9 belong to the union of those two sets. And then finally for this one, the interval. Right, and just like the first two examples, there are two pieces to this graph, right? Two separate pieces, so I'm going to write an interval for each and then just have the word or between them, or the union symbol to symbolize the word or. This one, there's no left end, so negative infinity to indicate that, comma, the right end of that first piece of the picture is at 4, and neither of those are solutions, right? 4 is not a solution, negative infinity is not even a number, so parentheses on either end. Or we have solutions, and again the union symbol for or we have solutions over here where, again, this piece of the graph, the left end is at 9, comma, the right end, there is no right end, so I indicate that with positive infinity, and 9 is not a solution, parenthesis, infinity is not even a number, parenthesis. Right. So here's an interval notation for that set. Again, all three of these things mean the same stuff. Right. They all represent the same set of solutions, the numbers less than 4 or numbers greater than 9. Okay, all right, so I just got a couple more, and I'm hoping we run into some different scenarios in these next two. I actually picked them out of a book, thinking that we'd come across a few scenarios. So far we've seen scenarios where the two sets didn't overlap and we're running in different directions, where the two sets did overlap and we're running in the same direction. Alright, let's just keep going. Alright, so I got another one here. So 3x minus 2 is greater than negative 5, or, again, I see the word or, that'll be in throughout. The word or will be in there throughout, and we'll be taking the union of two sets. Or 2x minus 5 is less than or equal to 1. Alright, so same thing every time. I solve each one separately, so this one left in orange again. You got I'm going to add 2 to both sides. 3x on the left now is greater than negative 3. Divide by positive 3. So I have x is greater than negative 1. So again, set A, the set of all the solutions of this first inequality, are all the values of x that are greater than negative 1. Alright, and the other inequality, I would add 5 to both sides first. We have 2x is less than or equal to 6, and then divide by 2. So x is less than or equal to 3. Alright, so the set B here is the solutions of all these of the second inequality are all the values of x. Alright, as long as those values are less than or equal to 3. Alright. And then we're going to take the union, right? I'm seeing the word or again. So first a picture though, right? First a picture, and then we'll talk about the union. So again, 0 somewhere, and let me actually put numbers in the proper place this time. So all the numbers greater than negative 1. So the negative 1's to the left of 0. And all the numbers greater than negative 1 would be these numbers here, right? Not including negative 1, right? All the numbers greater than to the right. There's set A. Set B, right, the solutions of the second inequality, all the numbers less than or equal to 3. Now positive 3 would be over here on this side of 0. Less than or equal to 3, right? So 3 is in there, 3 is in set B. And all numbers less than 3 would be 2, 1, 0, right? All these numbers over here, to the left forever. Alright, so this is a little different than our previous 3 examples. previous 4 examples actually, because yeah, they're pointing in opposite directions, but there is actually some overlap here. Right? There are some numbers that are in both A and B. Alright, so if you think about what's in the union, what's in the union of these two sets? It's going to be all x such that, and then we'll make a little description afterwards. Well, you could write, this inequality or that inequality. It wouldn't be wrong to write x is greater than -1 or x is less than or equal to 3, -3. But I'm not going to do that because you can see what I'm going to actually write a better description. Look at this. Can you see that every real number, every number on the number line is in the union? Pick a number. This number here is in set B, so it's in the union. -1, yeah, it's not in set A, but it is in set B, so it's in the union. This number here is in both. All these numbers over here are in set A. So all the numbers to the left of -1 are in set B, they're in the union. -1 up to 3 are in both, so they're in the union. And all the numbers to the right of 3 are in A, so they're in the union. Every real number is in the union. I am seeing that from this picture, right? Every real number is in the union of these two sets. So all I'm going to describe here, when I write down what is A union B, it's all the values of x such that x is a real number. Right? Just every single one, every number you can think of is in one of these sets. So therefore in the union. So here's a description of the solutions in that set builder notation. And then for the graph, right, when I graph the solutions, here's the number line, 0 and all that. Just said, every single number you can think of on the number line, every real number is in this set, this union. So I will simply just do this. Everything. Right, just everything to the right, everything to the left, everything. There's the graph. Everything is in the set of solutions. So there's a graph of your set of solutions. And then finally for the interval, all right, look at this, right? There's no holes in this graph. There's no gaps, no spaces. This is all one big piece, one continuous piece. So I'm only going to need to write one interval. And look at this piece. What's the left end? Well, there is no left end, so I indicate that, as I've mentioned, with -infinity, comma. And then as you go through the piece, is there a right end? No, there isn't, right? That goes to the right forever. So to indicate there's no right end, put +infinity. So -infinity, comma, +infinity. And then I've always mentioned too, you put parentheses around these because -infinity and +infinity are not numbers. So there's the interval notation for all real numbers. Right? You could also say all real numbers here, right? Our solutions. And go ahead, try it out. Go back to the original inequality, right? Our compound inequality, this guy up here with the or. Pick any number you want. Any number you want. 1, 2, 3, -5, 5,000, 2/3, pi, square root of 2, e, whatever you want. Plug it in, and one of these, at least one of these, will be true, so the whole statement will be considered true, the whole compound statement. Because remember what that or means. This is an inclusive or. So if this is true, or this is true, or both, we have a good solution. Any number plugged in will make at least one of these true. Fantastic. So that was an interesting scenario there. Alright, I've got just one more for you. See if anything else interesting comes up. Our last example And I'm going to go through the same steps, right? Solve each. I have the word or involved, and when the word or is involved, it will stay involved. And then we have a union. I solve each one separately, and then find the union of the two solution sets. All right. So same steps. Solve this one. I would first add 2, giving me negative 5x is less than or equal to 5. Then I would divide both sides by negative 5. Now here's the tricky part, right? You got to remember, when you multiply or divide both sides of an inequality by a negative number, right, the inequality changes direction. It flips up. So you have x is now, instead of is less than or equal to, is greater than or equal to, and then 5 divided by negative 5 is negative 1. Right, so be careful with that. So again, I'll call this set A. All right, so the set of the solutions for the first inequality are all values of x such that x is greater than or equal to negative 1. Or, and then we have the set of solutions for the other inequality, which I would just, add 9 to both sides. We have 7x is greater than 14, and then divide by positive 7, so the inequality won't change direction. It's a positive number I'm dividing by. X is greater than positive 2. Alright, so set B for the set of solutions for the second inequality is all values of x such that x is greater than positive 2. Alright, and as I've done with the past, with all the examples in this video, let's make a little picture of these sets on the number line. So again, here's 0, and in orange, set A, here's negative 1, and all the values greater than or equal to negative 1. So negative 1 is included, a little solid point, and all numbers greater than negative 1 are to the right. There's set A. And then set B, the solutions of the second inequality, all the numbers greater than 2. Now 2 is to the right of 0. And all the numbers greater than 2, but not equal to 2. So not equal to 2, a little open point down here. And then all numbers greater than 2 are this way. And what I have here is exactly the same as like my third example in this video. It's a while back now. Where the two sets are pointing in the same direction and actually overlap. Right? Okay, so now what's in the union? Right? What's in the union of these two sets? And it's going to be all values of x such that. Now you could write x is greater than or equal to negative 1, or, right, where the word or is here. You could write x is greater than or equal to negative 1, or x is greater than 2. That wouldn't be wrong to write. It's just that, do you see how one of those can kind of be just absorbed by the other? Let's take a look at this, right? You see how all these numbers here, right, all the numbers greater than 2 are also in A. Right? All of these numbers here are also in A. So it's almost like set, oh, I didn't call it set B, sorry. That's set B. See how all the numbers in set B are in set A already? So like you can almost say set B is absorbed by set A, and really the only numbers that belong to the union are in set A. Right? So you see all these numbers from negative 1 to 2 are in set A, so they belong to the union, and all the numbers afterwards are in both, so they belong to the union, right? It's either in A or in B or in both. So really the only numbers that matter here are in set A, because again the numbers in set B are absorbed by set A. They're already in set A. So really I just need to say that the numbers in my union are all the numbers that are greater than or equal to negative 1. Right? You don't need to write or the other one if you don't want to, because the other one is just absorbed by the first one. I hope that makes sense again, right? Just like the third example. All right, and check it out, try it out. Try some values. Plug in negative 1 for x's. Plug in any number greater than negative 1 for x's up here, and at least one of these will be made true, right? As long as this one or both is made true, the whole thing is considered a true statement. All right, so there are the solutions in set builder notation. And then lastly, we'll make our graph and interval. All right. So the graph of our solutions, the picture of them, here's the number line. Again, 0 somewhere, and then negative 1 is to the left of 0, and all the numbers, greater than or equal to negative 1, right? So there is a picture of our solutions. All those numbers there that I just drew are solutions of the compound inequality we started with. And finally, the interval This is another one of those graphs where there's just one piece, right? There's no other part of the graph over here. It's one solid piece. So I'm only going to write one interval. And looking at this piece, the left end is at -1, comma. Then there is no right end, right? So I indicate that with infinity. -1 is a solution. So the square bracket, the rectangular bracket around -1. And then infinity is not a number. Right, so always parentheses on that. And there you go. That's the interval notation for that set of solutions. All right, and again, as I've said in all these, all three of these represent the same set of numbers. They mean the same thing. All the numbers greater, they're describing all the numbers greater than or equal to -1, all the solutions of my original inequality, this compound inequality. Any number -1 or greater will make at least one of these two true, and therefore the whole statement true. Wonderful. All right, so that was a long one. All right, lots of examples there. So I think I had 6 examples where I did the same thing. Right, you see the word "or" connecting two inequalities. Solve each one separately, and then find the union, right, of the solution sets. What numbers are in one set or the other set or both. And you've seen a couple scenarios, right, that you might come across where they're going in opposite directions, the same direction with some overlap, or in opposite directions with some overlap. And just, find that union, and then you'll have the solutions of the compound inequality. And make a graph, write interval notation, write set builder notation, whatever you're asked for. Just read carefully. Okay, and as I like to say at the end of these videos, try your best to learn the material, understand the material on your own before you go looking for help. I find that the material tends to stick with people longer, and they remember it better, recall it better when they've taken the time and the effort to learn it on their own. So read the material, of course, read the author's examples, perhaps even try to work out the solutions to the author's examples before you see how the author did it, and then compare your work to the author's and see if you can learn from any mistakes there. And work on, of course, plenty of practice problems, exercises. Look for solutions whenever they're made available to check yourself. And don't just give up after the first attempt at a problem. There are usually several different ways to approach a math problem. So, if after several approaches of a problem you're still not getting it, then perhaps you should read the material again, more slowly, more deliberately. Take notes. Because, if you've worked on some problems, you probably have a better idea as to what the author is expecting of you. So then a second or even third read through of the material will shine some light on things that maybe you didn't see the first time. Maybe some things will click that didn't click the first time through. But if after that, if after several read-throughs of the material, after several attempts at problems, if you're still not getting it, still not clicking, then it is not a sign of weakness whatsoever to go out asking for help. That is what other people are there for. So ask a teacher, a tutor, a friend, someone in the class who knows the material and is willing to help. Look for supplemental materials online. There's tons of it out there. Look for videos on the subject, such as this one, or plenty of other ones out there that are better than mine. I assure you, you can find them with a simple search. But just keep at it. Stay persistent. Keep practicing. Don't give up. And I think the hardest part is to keep a positive attitude about the subject as well. It's very difficult to learn when you go in thinking you are going to hate it, or when you already feel like you're defeated and you hate it, and you always hated it. It's very difficult to get through something when you're thinking that way. It is amazing the difference a positive attitude can make. It's amazing the difference a change in attitude can make. I know it's easier said than done, but try to go in with an open mind, thinking I'm going to learn something today, I'm going to enjoy learning this, I'm going to use it in my life, I'm going to use it in my class, and I'm going to have fun and have a positive attitude about it. All right, that's the hardest thing, I know, but just try to do it. All right, just keep it in your mind, keep that mindset. Okay, so stay persistent, keep practicing, stay positive, don't give up, and I just know you're going to get it. And thank you for watching.